What's more interesting is that the character of the exciton is quite unique. So you look at the wave function, the electron hole amplitude for the lowest exciton state for this ribbon. It looks something like this. If I fix the hole at one position and plot out the square of the electron amplitude, and what you find is the hole and the electron, they are separated. And they are located on different edges of the ribbon. So this is a very interesting charge transfer exciton. And because you are taking an electron from a region where it is it's in a majority spin state to a region where it's actually a minority spin state orientation, then you actually, through this kind of photoexcitation process, you change the magnetization of the ribbon. So you might ask, ribbons are interesting theoretically, but will they actually be possible to make? When we first do this kind of calculation, we proposed that perhaps you could use electron lithography or chemical routes or splitting single wall carbon nanotube to make graphene nanoribbons. Of course, our experimental colleagues are really clever. In fact, they have all done all three of this, use all three of this means to get to carbon graphene nanoribbons. Here I just want to show you one very recent result by Hongji Dai's group at Stanford, where they use chemical means to make ribbons that's smaller than 10 nanometer in diameter. In fact, when they measure the gap of those ribbons, what they find is all the ribbons they make are semiconductors, and they can not able to see any metallic ribbons. And very, very recently, in April this year, the group at Rice and also the group at Stanford now able to actually split nanotubes to form graphene nanoribbons. So now you have a way really to make a well-defined straight edge nanoribbon. So we're very excited about this also. And I think I'm running out of time. Could I have maybe 5 minutes to discuss this? So I just want to discuss one more topic, which is how important this kind of quasi-particle and electron interaction effects on another system, which is the single molecule transport through single molecule system. So there are a lot of interest in molecular electronics in the last maybe 5 to 10 years. So the kind of system you would like to understand is transport of electron through a molecule when you make metallic contact to it. Now, because you have such a small size system, we know that the contact chemistry and the detail of the electronic structure will control the transmission or the conductance through such a system. And microscopically, of course, then what controls the transmission of the electron is the energy level and the position of the energy level of the molecule compared to the Fermi level of the metal. One of the major issues in the field, in fact, is the density functional based methods. When you calculate the conductance through such a system, give you conductance which often orders of magnitude too large compared to the measurement. And this is related to how well can you describe the molecular levels relative to the metallic Fermi level at a metal molecule contact. So if you look at an isolated molecule, you know that you're going to have a certain LUMO, the lowest unoccupied molecular orbital, and certain HOMO level relative to the vacuum level. However, as you bring the molecule next to the metal, those positions, those molecular level energies will change. So the question is, whether density functional theory will able to actually describe this kind of change correctly, because you know that the conduction through such a molecule will exponentially depend on the position of the level. And the changing of the level depends on a number of physical effects, interfacial charge transfer, quantum mechanical coupling between the molecular state and the metallic state, and electron correlation effects. Now, density functional theory, well, in principle and also in practice, will probably give you the first two right, but whether it could give you the third one right is problematic. In fact, we find that the DFT levels are not adequate at all. So let me just show you one simple example. This is a case of benzene on graphite. So that's the simplest possible metallic organic molecule system you could look at. So you look at an isolated benzene molecule. Within LDA, you get a homolumo gap around 5.1 volt. Within GWA, you actually have a gap of 10.5 volt. So it's a very large difference. Experimentally, this gap can be deduced by looking at the difference between the ionization potential and electron affinity, and give you an experimental number somewhere between 10.4 to 10.6. So LDA underestimates the gap of the molecule by a factor 2. The GW gap actually is quite good in agreement with the experiment. In fact, it also gives you a LUMO above the vacuum level. Now, suppose you put benzene on graphite. Now, within LDA, actually not much change. You still have a gap around 5.1 electron volt. In the GW calculation, you have a gap, or homolumo gap, of 7.3 electron volt compared to the isolated molecule of 10.5. So you see that as you bring the benzene molecule toward the graphene surface, you actually reduce the gap by 3 volts. But LDA doesn't really give you the right answer because it's off by 2 volts. Even more important is that if you look at how this homolumo gap in alignment of the level with the metallic Fermi level as a function of the geometry, that is, you bring in the molecule either flying flat or perpendicular to it and so on. You see that in DFT LDA, there's hardly any difference. In fact, we have done calculations using GGA and other hybrid functionals. In general, it gives you very little dependent on geometry. However, the GW calculations show that there is significant dependent on geometry because it's related to the electron, the correlation of the electron, the quasi-particles in the molecule with the electrons on the surface. So this kind of changes from the LDA value come from intermolecular exchange and correlation, and also interfacial polarization. And here I just show you that this kind of effect doesn't go away with bigger molecules. Here is looking at the homolumo gap for isolated arsenes going from benzene to pentacene, and compared to the gap on graphene. And what you see is that this change, in fact, is really doesn't change with the size of the molecule. And there actually good experimental evidence on this kind of interfacial polarization or correlation effects. Recently, there have been some STS experiment of looking at the homolumo gap of pentacene with layers of sodium chloride, an insulating material in between copper and the molecule. So you see that as a function of the number of layers, it converges to the isolated molecule phase case. So you see that indeed the interfacial interaction, this kind of screening effect is very important. So let me just show you some results as a consequence of this kind of quasi-particle corrections on the conductance of transmission through a molecule. This is for a series of molecules that we have looked at, comparing the calculated conductance with the experimental conductance. The calculation is done through using the Landau formalism. And you see that the calculated results are in general order of magnitude too large compared to the experiment. And the reason is because the homo-Reaumur gap is too small, and you make the conducting channel too close to the Fermi level of the metal. And you include the self-energy effect. In fact, it immediately gives you a much better agreement between theory and experiment. Because as you move the conducting channel away from the Fermi energy of the metal, this changes the conductance in an exponential way. Okay, so I think I've taken enough of your time. Let me just conclude with acknowledgement to all my collaborators. The work done on single molecule junction is with Sweeting Park, a postdoc of mine, Jeff Nitton, Mark Ibis, and Hong Jun Choi. The work done on graphene and graphene nanostructure is with several really excellent students and postdocs, and also with Marvin Cohen. And then the work on carbon nanotubes is also with several really excellent students and postdocs. And many of them have now left Berkeley to go on to better things. Thank you very much. I'll be glad to answer a question if you're not too hungry.
Question regarding the bandgaps in armchair nanotubes. No, nanoribbons. And there are three families, like 3+1, 3+2.
Yeah, it's pretty easy to understand. In fact, it's related to you had to fit a wavelength of an electron to. If you look at the wave vector along the direction of the length of the ribbon, of course you could take any volume, but along the direction perpendicular to the length of the ribbon, then the wavelength of the electron has to fit in. So the simplest level, that means you should chop up the state of graphene into states. The allowed states are the states that could fit in. So you look at it very carefully, you will find that there are actually three families. And just like carbon nanotubes, a third, in the simplistic picture, a third of them are metals. So basically it comes to that.
Band folding.
Yeah, basically a band folding type of picture.
Any questions?
Yes, definitely.
And a question about this photoexcitation. So these magnetic excitations induced by light on nanoribbons.
Mm-hmm.
We were mentioning where a case where the hole would stay on the minority spin side and the electron on the majority spin side, or the other way around.
Yeah, what happened is that you have the ground state. The states that involve in the transition are edge states, right? So before the excitation, you would have the occupied states. There are two edge bands. One will be spin up localized on one edge, another one spin down localized on this edge. So when you do a photoexcitation, you cannot flip the spin of the electron. So you have to take the electron, will spin up to an empty state, will spin up. The empty state will spin up has to be on this side, right? So that's why you have a charge transfer exciton. The hole remain on this side, which on the, let's call that spin up side, and the electron now go to the spin down side, so it cancels some of the magnetization on this side. So a photoexcitation will reduce the magnetization, and also explains why there's this transfer.
So it reduces the magnetization on one side, because the total magnetization has to be conserved by selection rules, right? So the total spin of the system cannot be changed by photoexcitation.
That's right. But the total spin of the system is zero anyway, because it's an antiferromagnetic system. So what you're doing is you're reducing the magnetization on one edge,
and you increase it on the other.
Right. Yes?
As you go from single one nanotube to multi-one carbon nanotube,
Yes.
how these excitonic levels and these excitations differs?
I think that is a very good question that no one has done a detailed study, both theoretically nor experimentally. Just the last 2 or 3 years, people were able to make well-defined double-wall nanotubes. These are the Japanese group, Endo's group. And this kind of excitonic calculation is quite time-consuming. And GW calculation, we have a computer code that we optimize. Now we could do several hundred atoms in the unit cell. And even with that, we are just beginning to study double-wall nanotubes. One would expect that excitonic effects still would be very important for the semiconducting carbon nanotubes. But I don't know whether it will be remain very important for the metallic carbon nanotubes. But I would expect that it's still very strong in the double wall carbon nanotube, and also it will become much more complicated because you could involve states mixing in many different states.
Any more questions?
Yes.
Okay, properties of nanoribbons. Do you assume like a perfect geometry with like a straight in edges and without any stress on the edges?
The results I showed you are basically due to just straight, homogeneous straight edges. We have also looked at defects on, in particular, the magnetic case. We want to know how robust magnetism is. Then we actually introduce defects on the edges and so on. It turns out that it's very robust, and you could introduce up to 5-10% of defects and still retain this edge state and magnetism. We also, I didn't have time to show you, we also have done some calculation on nanotube metal contact. Use a nano ribbon as a channel for conduction. Then it turns out that it's quite complicated. By changing the edge a little bit, you could actually change the conductance quite a bit. So in terms of application of graphene ribbons for nanoelectronics, one really have to solve this edge problem, the defects in making good edges. So that's why it's exciting that now they could split carbon nanotubes to form nice ribbons. At least we could study the ribbons and then see how defects changes the property of the ribbons.
Any other questions?
Oh yeah. You showed that you have quite different properties for the zigzag and the arc nanoribbons. And I was just curious why. I mean, in some sense, it seems like they're both finite chunks of graphene with different edge terminations. And so I was wondering, is there a simple explanation for why the properties are different, or is it just the particular states that you remove when you?
There is actually, just like you look at semiconductor surfaces, the 100 surface is very different from the 110 and 111 silicon surface, for example. So the zigzag edge, in fact, topologically very different from that of the armchair edge. And it's this particular zigzag geometry you could work out within a simple type binding model that there's no interaction between the A sublattice and B sublattice at the capital K point. So that gives you a very very small interaction between neighboring edge atoms, and that's why you have flat edge states. Very similar to the case of the 111 surface of silicon. So it's really the topology of the bands that give rise to it. So it's not just that it happened. Yes?
I have a question about the application of GW to single molecule junctions.
Yeah.
So, if I understood correctly, you apply GW to the molecule only, or to the whole system? Because I think that if you apply GW to get a better gap in the molecule, maybe this could modify also the charge transfer and the coupling properties with the leads, and so you should do it self-consistently.
Right. So that's why in the figure I have put sigma with a quote on it. What we have done is we do the GW on the molecule, and we introduce the molecule to the substrate, and we look at the modification of the homo-lumo level. And then we use that in a scattering state calculation that effectively put in a U on the molecular levels to do that transport calculation. So we have not done a true GW calculation for the full metal molecule metal system. But I think to a good degree that would give you the major correction, the first order correction to the problem we're looking at. Because we are 2 order of magnitude or 3 order of magnitude off compared to experiment. So the self-consistency and all that thing should be taken care of eventually, because as you say, if the levels are moved further or closer to the Fermi level, charge transfer will be different and so on. We haven't really taken that into account.
Yeah.
In the GW calculations, I think the conduction bands not compacted and they will change behavior. For example, we have calculated the band structure of something in LDA and GGA and corrected with GW calculation. Do the behavior of the conduction band improve much or just the gap changes?
I'm not sure I understand your question. Usually what happens when you do the GW calculation is that both the conduction band and the valence band move in terms of the energy position. Now, whether the amount of movement will different from the mean field you start with. We have actually start with Hartree-Fock, and what happened is the gap reduced to the more closer to the experiment. You start with LDA, it opens up, and then you start with LDA plus U, it will do something in between. So it will modify the energy of both the valence band and the conduction band, and how much it modifies will depend on the mean field you choose to start your calculation with. But as long as you choose a reasonable mean field, you should get a reasonably good answer. This is a matter of perturbation theory. You will start with a reference Hamiltonian which is too far from your final result, then your perturbation theory doesn't work. So that's why we're actually working on improving our starting point for GW calculation for the more correlated electronic systems. So we have looked at LDA plus U and other starting points.
Okay, maybe one last question. Okay.
Okay, so you have just mentioned the strong correlated system. So do you think that GW will be successful for strong correlated system, like say the multi-iterator or the link optimizer?
Well, depending on what question you want to address.
But just for the band gap.
Just for the band gap, yes, it will work very well because we have looked at things like nickel oxide, and we have looked at model system like BCC hydrogen. You need to build in the antiferromagnetism into it. What I'm trying to say is that there are certain properties that GW will describe well, for example, the gap. But whether you could get out the details in the spectrum, the spectral wave function, for example, one might not be able to get it out correctly. In fact, for the BCC model hydrogen system, we compare our results with quantum Monte Carlo calculation. It agrees quite well. So at least for that particular Mach transition, where we restrict ourselves to an antiferromagnetic insulating phase, it seems to work very well. But it really doesn't mean that GW will work, for in general, because we know that it has its limitation. It's just a first turn in expansion, right? So it's going to break down sometime.
Okay, that's Louie.